Hello, am I audible?
Yes, sir.
Abdul Wahid? Please reply. Should we start? Okay. So first chapter of second part is mechanical property of solids. I'm defining you some of property. Suppose you have a support and there is a spring attached with it. So the length or the natural length of a spring would be of this length. If you extend it or compress it, like if you compress it till this position, or if you extend it till this position, a force will develop in this particular spring, which will tend to restore the actual length of spring. So it will be along this direction. And for this length, it will be along this direction. So this force, which develops due to compression or expansion of spring to return back to its original position, is termed as a restoring force. And the tendency by which this force is arising in this particular spring is termed as elasticity. Is it clear?
Yes, sir.
Abdul Wahid, suppose the actual length of this particular spring is this much amount, let's say L naught. If you compress it to this particular length, or if you extend it to this amount of length, there will be a force developed in this particular spring, which will tend to restore its original length. That force is termed as restoring force, and the tendency by which this force is arising due to compression or expansion in this particular spring is termed as elasticity. So we first define what do you mean by elasticity. So you'll say all of rigid body, suppose there is an era of molecule which are arranged on a corner of a cube. An atom at this point, this point, this point. These are some atoms, and they are held together by some bond which may have some spring-like property. That's why I'm drawing like this. Now, if you apply any deforming force to any of its atom, let's say at this upper corner, so it will extend along this line, along this line to this point. Now, due to elastic nature of this particular bond, there will be a force developed on this particular body, which will tend to restore its original tendency or original configuration or shape. This tendency of body to regain its original shape on removal of deforming force is termed as elasticity. So if you apply any deforming force to deform the shape of any object, there will be a force which will tend to regain its original configuration. That tendency of body is termed as elasticity. So elasticity is nothing but the tendency of body to regain its original shape on removal of deforming force is termed as elasticity, and opposite of it will be termed as plasticity, which means if a body having no tendency to regain its original configuration on removal of deforming force is termed as plasticity. Is it clear? Yes, Abdul Wahid?
Yes, sir.
So the inability of a body so that they can't regain its original shape on removal of deforming force is termed as plasticity. In general, the tendency of a body would lie in between elasticity and plasticity. There will be no rigid body which is perfectly elastic, and there will be no rigid body which is perfectly plastic. So the property of body would lie in between elasticity and plasticity. The property of body will lie in between elasticity and plasticity. Is it clear, Abdul Wahid? Okay, just write it down.
Done, sir.
Go ahead, you have written. Okay. Why you have written? Okay. Now, depending upon these two properties, we may define some term in this chapter. First is stress. Suppose there is a solid body which is hanged by any support, and if you apply any deforming force to this, let's say this is deforming force which is applied to this particular rod to change its shape. Due to that deforming force, it will get extended by some length along this direction. Suppose the initial length of body is this much, and the extended part due to this deforming force is this much. Area of cross section at this particular point is E. So stress is mainly the ratio of deforming force applied per unit area to that particular rigid body is termed as stress. So stress is nothing but the deforming force applied on a body per unit area is termed as stress. So there will be any angle related to this force and related to this particular area. There is no specific direction of these two terms. Whether force will be normal to that particular area, whether it will be tangential to that particular area. So we may define stress in different types. So first is stress is nothing but ratio of deforming force divided by area of cross section. So SI unit of force is Newton and SI unit of area is meter squared. So it will be SI unit is Newton per meter square. Is it clear?
Yes, sir.
Now, due to this deformation, the rod has extended by dl amount or delta L amount with respect to this original length, that is L. So we may define another term that is called strain. So strain is mainly the ratio of deformed shape in that particular body to the original configuration of that body. So we have to relate them. So we define another quantity that is strain. The ratio of deformed shape to the original shape of body is termed as strain. So strain equals to deformed configuration, whether it be along length, it will be along angle, it will be along area, along volume, or any deformation, divided by actual configuration or shape of that particular object. So in numerator and denominator, we both having same quantity, so it will be unitless quantity. It will be unitless quantity. Abdul Wahid, is it clear? Or do you have any doubt in stress and strain?
Sir,
Okay.
in stress, then it will be delta L divided by L.
No, it will be in strain.
Okay, then in stress.
Stress, it will have force divided by area. So force over area.
Okay.
I will define its type, then I will define its formula related to those terms.
Done, sir.
Why you have written? Okay. Now there is relation between stress applied to this particular object and the strain produced in this particular object, which is termed as Hooke's law. It was Robert Hooke who discovered cell first. So in this Hooke's law, it tells you within elastic limit, I will define you what do you mean by elastic limit. And at constant temperature, the more you apply stress to that particular object, the more strain will produce or develop in this particular object. But it will be till elastic limit related to that body. So we can say at constant temperature and within elastic limit, the strain developed in a particular object will be directly proportional to applied stress. The more you apply the stress, the more deformation will produce or the more strain will develop in that particular object. So the strain produced in the body is directly proportional to the applied stress. So mathematically, we may write it as stress is directly proportional to strain produced. So if you replace this proportionality sign by placing any constant term, so it will be stress equals to some E times strain, where E is called modulus of elasticity. And if you draw a curve related to stress and strain, let's say stress is along vertical line and strain is along horizontal line. Since stress and strain is directly proportional, so there will be straight line in between these two terms. Now, If you rearrange this particular equation, you will get E equals to stress divided by strain, which is nothing but ratio of perpendicular and base. So according to this graph, this will define you slope. Suppose this line is inclined at some angle theta. So if you find tan theta, it will define you modulus of elasticity or simply the value of E. Is it clear?
Yes, sir.
Abdul Wahid, any doubt in this Hooke's law? Hooke's law simply defines you relation between stress and strain, but there will be at some condition. First is temperature should be constant, and next is it should be within elastic limit. I will define you later what do you mean by elastic limit. The amount of strain or the deformation produced or developed in that particular body will be directly proportional to amount of stress applied over that. Is it clear?
Yes.
Wahid? Okay.
Sir, in this chapter, what are the derivations?
There will be one or two derivation in this chapter. First is potential energy in a wire, and the rest of the thing will be basically numerical part. I will define you
Okay, sir.
all of the problems. It will be subjective or objective.
Subjective, sir, because it's second term, right?
Okay, okay. Wahid, you have written? Now, depending upon these three terms, we may divide it in different types. Okay. So first is longitudinal or compressive stress. Suppose you have a body which is attached to any support, and if you apply any deforming force, let's say to extend this part, or let's say to compress this particular object. Due to that deforming force, this body has deformed by this much amount. Original length of object is this much, and deformed part is this much. Original length of body is this much, and deformation will be till this part. So in terms of elongation, let's say in first part, it will be termed as longitudinal, or in terms of compression, it will be termed as compressive. Both are same, simply they are differ only in direction. Is it clear?
Yes, sir.
So longitudinal stress is amount of deforming force applied per unit area. So stress will be force divided by area. It will be either to elongate that particular body or to compress that particular object. So we may define it as longitudinal or compressive stress, depending on that. Force having unit as Newton, area having unit meter squared. So SI unit is Newton per meter square. Similarly, we may define strain related to this, which will be termed as longitudinal or compressive strain, or let's say longitudinal strain. So longitudinal strain equals to amount of deformation produced, that is delta L, divided by actual length of that particular object, L. Both having same unit in numerator and denominator, so you'll say it will be unitless quantity. Now, if you apply Hooke's law related to these two terms, there will be a term that is called Young's modulus, which is nothing but ratio of deformed shape ratio of longitudinal strain by longitudinal strain. In above part, I defined you modulus of elasticity, which may be divided into three different parts depending upon stress strain. So in first term, for longitudinal stress or compressive, modulus of elasticity is termed as Young's modulus, which is equals to the ratio of longitudinal stress to the longitudinal strain. If you put it in numerical part or mathematical term, Young's modulus Y equals to longitudinal stress F divided by area, longitudinal strain delta L divided by L. So it will be F times L divided by A times delta L. This Young's modulus will define you elasticity of that particular object along length. So it will be also termed as elasticity of body along its length. It will depend upon two factors. First is temperature and the second is nature of material. So all of modulus of elasticity will depend upon two factors. First is nature of material and second is temperature. So you may write here E depends upon temperature and nature of material. It will be independent of dimension of body independent of dimension or deformation produced. Is it clear?
Yes, sir.
Just write it down to this part.
Done, sir. Amona, you have written. Yes, sir.
Wahid, you have written. A wire of 2-meter length is extended by force of 2 kilonewton. Find stress and strain if Young's modulus is 2 into 10 raised power 11 Newton per meter square, and area of cross section is 4 mm square. In this part, we have force F equals to 2 kilonewton. Kilo means 10 raised power 3, so you may write it as 2 into 10 raised power 3 Newton. Length of wire is 2 meter. Area of cross section is 4 mm square. First of all, we have to convert each quantity in terms of SI unit. We have mm square. So if you want to convert it in terms of meter, just multiply it by 10 to the power minus 6. So it will be in terms of meter square. Now the next term is Young's modulus is 2 into 10 to the power 11 Newton meter square. Now apply the above formula and try to find stress, strain related to these given quantity. Stress is equals to amount of force over area of cross section. Try to solve. Just put the value to find the stress. To find stress, force is 2 into 10 raised power 3. Area of cross section is 4 into 10 raised power minus 6. So 2 divided by 4, it will be 0.5 into this 10 raised power minus 6. Moving on to numerator, it will become plus 6. So it will be plus 9 Newton per meter square. Is it clear?
Yes.
Now, how to find strain? In this given part, we have only L. We don't have delta L. So for strain, there is formula delta L divided by L. So we don't have delta L in this part. So we may use related to Young's modulus, which is equals to stress divided by strain. So strain will be equals to stress divided by Young's modulus. Stress we have found 0.5 into 10 raised power 9, and strain is 2 into 10 raised power 11. So if you divide it, you'll get 0.25 into 10 raised power minus 2 meter. No, it would be unitless.
So in the stress, what did I do is when we cancel 2 and 4, we get half, right? So I separated 10 to the power of 9. I wrote it 10 into 10 to the power of 8 divided by 2. So I can cancel 10 and 2. So it becomes 5 into 10 to the power.
Good. You have shifted this decimal to right side. Then power will become 8 Newton per meter square. You may write this. Now, if you put them in this part, you will get 2.5 into 10 raised power minus of 3. Is it clear?
Yes.
Now, from this part, we may define the amount of deformation developed in this particular wire by using strain equals to delta L divided by L. So if you have to find delta L, so it should be L times strain. Length of wire is 2 and delta strain is 2.5 into 10 raised power minus of 3. So 2 into 2.5, it will be 5 into 10 raised power minus 3, or it will be just 5 mm. Is it clear?
Yes.
Okay. Wahid, is it clear? Wahid, you have written? Okay. Now there will be some other question like, suppose you have any support and there is a wire from this part to this part, a block having mass 3m attached to this particular rod, another rod having mass 2m. So this rod having length L, this rod having length L. Let's say Young's modulus is 1.5 into 10 raised power 11 Newton per meter squared, and Young's modulus of this wire is 2 into 10 raised power 11 Newton per meter squared. This is wire A and this is wire B. So you may have to find the ratio of stress strain. Try to solve. If both wires have same length and same area of cross section. If wires are identical, which having same area of cross section and having same length. Mamuna, is it clear to you?
Yes, sir. Sir, one thing I have question that this 3 meter and 2 meter is what dimension? For what?
3m. 3m is mass of that particular block and 2m is mass of that particular block. So
Okay.
mass is 3m and mass of block is 2m. Let me give you some hint how to approach this problem. For stress, we first need amount of deforming force acting on that particular body. So in this part, this block will be responsible for applying force on that particular string due to acted by gravity. So there is a concept of tension. So first, let me define you. What do you mean by tension? Mamuna, do you have any idea? What do you mean by tension? Suppose there is a support from which a wire, string, or rope is hanged freely. So it will be like this, or you may say it will be in slack position. Now, if you join a block at this end, now this string get straightened. So if you apply the forces acting on this particular system, so you'll say, due to mass of this block, there will be a force by gravity in vertically downward, that is mg. So to balance that particular gravity, there will be straightness in this particular string, and the point of junction along upward direction, this force will be termed as tension. So tension is nothing but a force which develops in wire, string, rope due to its straightness in opposite direction at the point of contact is termed as tension. Is it clear?
Yes.
So tension is nothing but a force which develops in wire, rope, or string due to its straightness is termed as tension. It will act opposite to the point of contact. It will act opposite to the point of contact. And next property is for maskless, inextensible wire, rope, or string, it will be same at each point. And next is for maskless, inextensible, it will be same at each point. Wahid, is it clear? What do you mean by tension? Now, according to this concept, if you may define force on this block, so there will be a force along downward direction due to 2m mass. So it will be 2m times gravity. To balance this, there will be tension along this direction. Let's say T1. So at this point, total upward force and total downward force will be equal as there is no movement in this block. So T1 will be equals to 2 times of mg. And this will be responsible for stretching or deforming this particular string or wire. So this will be termed as deforming force. Now, if you apply similar to this above part, there will be tension at this particular point of contact in downward direction. Now the block having mass 3m, so there will be another force in this direction due to this 3m mass. Now to balance this, there would be some tension T2 in upward direction. Now from this part, we may write T2 equals to T1 plus 3 mg, and T1 is further equals to 2 mg. So on combining, you will say total force will be 5 mg. Is it clear now?
Yes, sir.
Now, stress on first wire divided by stress in second wire equals to force in string A, that is tension, divided by its area, tension divided by its area. Area is same, so these two will cancel out. T2 is 5 times of mg and T1 is 2 times of mg. So mg and mg cancel out. So you'll get 5 is to 2. Is it clear?
Yes.
Okay, just write it down. Muna, you have written?
Yes, sir.
Wahid? Okay, try to solve the second part, how to calculate the ratio of strain. In this part, if you apply to solve strain, a ratio of strain, as we know, Young's modulus is equals to stress developed by strain. So strain will be equals to stress divided by Young's modulus. Now let's say this is for A, A, A. Similarly, strain in B, it will be stress in B divided by Young's modulus in B. Now, if you simplify it, you will get stress in A divided by stress in B multiplied by Young's modulus in B divided by Young's modulus in A. Denominator of denominator will move to numerator. Now put the value of each term. Stress in A divided by stress in B, we have calculated as 5/2. Young's modulus of A and B is given as 1.5 and 2. So it will be 2 divided by 1.5 into 10 raised to power 11 into 10 raised to power 11. Now, if you simplify it, 2 and 2 will cancel out. 10 raised to power 11, 10 raised to power 11 will cancel out. If you remove this decimal, there will be 10, 5 into 2, and 5 into 3. So you will get 10:3. Is it clear? Mamuna
Yes, sir.
is just write it down. Abdul Wahid, do you have any doubt in this calculation? Good.
Sir, but when we divide 5 divided by 1.5, we get 3.33. So if we round off, we get 3 divided by 1, right?
You have divided 5 by 1.5.
Yeah.
So 1.5, it will be 3.33, like this,
Yes, sir.
which is similar to 10 is to 3.
Yeah.
Wahid, you have written? So this is all about Young's modulus and one-dimensional longitudinal stress and strain. Similarly, we may define the second term, that is tangential or shear. Suppose you have a cylindrical body whose base is fixed. So if you apply a force to this particular surface to deform its configuration, let's say it will move or it will tilt it along this direction. On applying deforming force along this direction, it will slightly bend along this direction. So there will be area of this top surface, let's say A. Due to this applying force, it gets deformed by some angle theta, and displacement from its original part will be x. Length of this particular cylinder will be n. Is it clear? Or do you have any doubt in this diagram? Mamuna?
Yes, sir.
So in this part, I've just applied a force tangential to this particular surface, and its base is fixed by any rigid support. So it will get slightly deformed along its inclination, let's say by some angle theta. So first is shear stress. So it will be amount of tangential force applied on that particular object per unit area is termed as shear stress. So in this part, force is tangential to that particular area of cross section. Now the corresponding strain developed is termed as shear strain. So it will be just theta, which may be equals to length of path divided by its radius or perpendicular by base, according to the concept of measuring radian angle. Now, if you take the ratio of these two terms, you will get modulus of elasticity in this part. That will be termed as shear modulus, which is equals to shear stress divided by shear strain. So modulus of elasticity in this will be denoted by G equals to shear stress F tangential over area of cross section divided by shear strain theta. So it would be F divided by A, theta equals to X by L. So this will be shear modulus. Now this G will define you elasticity in shape of that particular object. So this may be termed as elasticity in shape. Is it clear?
Yes.
Wahid, any doubt? Okay, just write it down.
Done, sir.
Abdul Wahid, you have written? Okay. Similarly, we may define third part that is called volumetric or cubical. Suppose you have sphere, and if you apply pressure to this particular object, due to which it gets slightly deformed. So force from this direction, this direction, this direction, and this direction. Since this force will be perpendicular to the tangent at the point of contact, so it will be perpendicular to area of cross section. So we may define this particular force by area as pressure to this particular object. Due to that pressure, there will be deformation along volume to this particular sphere. So I have taken sphere on which force is applied from all of its side to change in its volume. So we first define volumetric stress. So that will be force perpendicular over area of cross section. So it will be change in pressure or pressure to that particular body. Amount of deformation produced is termed as volumetric strain. So that will be delta V divided by V. In this part, since volume is decreasing, so final volume will be smaller than initial volume. That's why there will be negative sign here. Now, if you divide these two terms, you will get modulus of elasticity. In this part, it is termed as bulk modulus. So bulk modulus equals to volumetric stress divided by volumetric strain. Bulk modulus is represented by beta. Volumetric stress is F perpendicular over area of cross section divided by volumetric strain is delta V divided by V. F perpendicular per unit area will be change in pressure divided by change in volume into V, negative sign. So this will be termed as bulk modulus. So from this, we may define bulk modulus as, it defines you compressibility or rigidity of that particular object. Is it clear?
Yes, sir.
Okay, just write it down.
And
Wahid, you have written? Okay, let me give you some question. On applying 2 into 10 raised power 5 Pascal pressure to a solid, its volume get decreased by 10%. Find value of bulk modulus. Try to solve. Mamuna, any doubt in this question?
No, sir.
Just see in this part how to approach this problem. We have pressure equals to 2 into 10 raised to power 5 Pascal. And percentage change in its volume, we may write it as delta V divided by V into 100 is equals to 10. And since it is decreasing, so there will be negative sign. Now we have to find delta V by V from this part. So move this 100 to the other side. You will get minus of delta V divided by V equals to 10 over 100. So this 0 and this 0 will cancel out. So you will get 1 over 10. Now, if you apply the above formula to get beta, it will be minus of pressure or change in pressure divided by delta V by V. Pressure is 2 into 10 raised to power 5 divided by change in volume is 1 over 10. So minus and minus will cancel out. So you'll get value to be plus. This 1 over 10 or this 10 will move to numerator. So you'll get 2 into 10 raised to power 6 Newton per meter square. Good, Mamuna. Wahid, is it clear? Wahid, you have written till this part? Okay. Now there will be some other question as well. Which one will be more elastic? First is rubber and steel. Second is water and gas. So how to define these type of problem using mathematical relation? So let me define you how you can solve mathematically. For first part, just assume, let's say this is your support from which a rubber and steel of same length is taken. Mamuna, I have asked you how you would define which one will be more elastic. So you have to prove it mathematically. Okay. So let's say in first part, I have taken this as rubber and this as steel, both having same length L and having same area of cross section. Now, if you apply deforming force on each of them, let's say on this part as well as on this part. So if you apply same deforming force on either of one of them, so which one of them will get extended in more amount? So you will say rubber will elongate more. Now, elongation in rubber will be till this part. Let's say delta L in rubber, but steel will get elongate only to this amount. So this will be elongation in steel. So you'll say Young's modulus is equals to force times length divided by area of cross section into delta L, which means Young's modulus is inversely proportional to delta L. So the smaller the deformation in that particular object, it will have more Young's modulus or the value of Young's modulus, which will define you elasticity in that particular object. So you'll say, since delta L in rubber is greater than delta L in steel, therefore, Young's modulus of rubber will be lesser than Young's modulus steel. Hence, steel is more elastic. Is it clear?
Yes, sir.
So this is how we can approach this problem mathematically. Similarly, you may approach for the second part. You may say, suppose I have taken water and gas in a balloon having same volume. So if you apply same pressure on either one of them, gas will compress more as compared to water. So the more the deformation in that particular object, it will have lesser value of modulus of elasticity, which means it will have smaller elastic behavior. Is it clear?
Yes, sir.
Okay, just write it down. Wahid, any doubt till this part? Okay.
Done, sir.
Wahid, you have written? Okay, so this is all about the first introductory part of these three different concepts. Now we have to apply or define first stress strain curve. You'll be asked in school to define this particular curve. Suppose this is longitudinal stress, and this will be corresponding longitudinal strain developed in that particular object. So if you apply longitudinal stress to that body, it will first stretch linearly to this point. So this will be O and this will be A. If you remove deforming force from this point, it will retain its original configuration exactly, or it will return back to its initial configuration on removing deforming force from this part. Is it clear? It means it have some tendency to regain its original configuration that will be termed as elasticity. Now, if you further extend it by a little amount, it will move towards this direction to reach at some point B. Now, if you remove deforming force from this point, it will not go to its original position, but it will have a small deformation to this point from its original part. And it will be about 1 to 2% of its total length, and that will be termed as permanent set or permanent deformation in this particular body. Is it clear?
Yes, sir.
Now, up to this B point, body has tendency to return back to regain its original configuration. That is the property of elasticity. But if you further extend it, By deforming force, it will reach or it will move along this direction till this part. Now it has lost the ability to regain its original shape, and this term is known as plasticity or plastic behavior. So in this term, it has the property of plastic behavior. So this is called plastic region from B to C. And the object has elastic behavior from O to B only. So this is called elastic limit. And this B, up to which it has tendency to regain its original shape, is termed as yield point. In this region from B to C, it has lost the ability to regain its original shape, that is termed as plastic region or plastic limit. At this point C, the body has tendency to withhold maximum stress. That will be termed as ultimate stress. Now, if you further extend it from this C point, it will start flowing without any application of stress. And this point D, it will get broken up. So from this C point to D point, it will be defined as having tendency of flow or fluidity, and this D point is termed as breaking point. Is it clear?
Yes, sir.
Abdul Wahid, any doubt from this graph? Similarly, if you may compress this particular rod by applying any compressile stress to this, so it will again move along this path to reach at this point, to this point, to this point, and will may flow to break at this point. So in this above part, we have longitudinal stress. Similarly, there will be some compressile stress would may apply to this particular object to compress it like this. Now we have to define these points related to this curve. So first is O to A. If deforming force is removed, body will attain its original shape. From A to B, which is called permanent set, body has tendency to regain, but having some permanent deformation. From B to C, it has lost the ability of regaining its shape, that is termed as plastic region or plastic limit. So from B to C, object will have plastic behavior. It had lost elasticity. And from C to D, it will start to flow and break up and any contradiction. First, write it down to this part. I think only one more topic, that is potential energy stored in wire, which is derivation or the only derivation in this chapter. So either this question or that derivation will be asked.
Turns. You have written to this part? Yes, sir.
Go ahead. Okay. Now, depending upon this graph, you may be asked first, you must have learned in class 10th about two property of metal, that is ductility and malleability. Ramuna, what do you mean by ductility?
A substance which a wire actually which can be bent easily.
To bend easily. And what about malleability?
I think ductility is something which which can deform by tensile strength. I'm not
Okay,
sure.
okay. The property of a body to be drawn into thin wires on beating is termed as ductility, and the property of body to be drawn into thin sheets on beating is termed as malleability. So ductility is to be drawn into thin wires on beating, and malleability is to be drawn into thin sheets on beating. And there is one more property, that is brittle nature. The property of body to be broken into fragments on beating is termed as brittle substance. To be broken into fragments on beating, or on applying stress. So for ductility and malleability, plastic region should be longer. And for brittle substance, plastic region should be smaller. So you'll say these two property will be directly proportional to plastic region of that particular metal, and this property will be inversely proportional to plastic region of that particular object. So greater the plastic region of body, it will have more tendency of ductility and malleability. That's why gold is most ductile and most malleable. Is it clear?
Yes, sir.
Or you'll say gold having maximum or longest plastic region. Brittle means just like glass, which may be broken into fragments on a small stress applied over it. You have written till this part?
Done, sir.
Wahid, you have written? Okay. Just remember one more thing in this part. For perfectly rigid body, there will be no deformation in length, volume, or area. So these two terms will be zero. It means Young's modulus, shear modulus, or bulk modulus will be infinite. So you may be asked to define Young's modulus, bulk modulus, or shear modulus for perfectly rigid body. Just write it down. So let's stop here. I will define you one more term in next class, and then we'll continue mechanical properties of fluid. Okay, Mamuna?
Okay, sir.
Okay then.
Thank you, sir.
Thank you. Wahid? Just 1 minute, Wahid.